This is video 1.3. It deals with pressure. We're still very much in this area, so particles colliding is a really important idea. We've looked at particles, we've looked at state in the previous two videos, and now we're looking at pressure. So pressure, to repeat again, comes from collisions. So this is really the key thing to emphasize. Particles colliding exert a force, and that leads to pressure. So particle motion via collisions leads to pressure on a given area, but particle motion also leads to temperature, the idea of the small scale kinetic energy. The faster a particle rushes around, the greater the temperature. And we're going to have a look at the effect of fast compression there as well. So pressure then can be inside or outside. So inside pressure, if we decrease a container volume or increase it, it will affect the pressure inside. So decreasing it, the volume increases the pressure. Then if we look at outside pressure, so pressure coming inwards, that will also affect gas volume, so an air bubble being the key example there. Now pressure also changes with depth, so in water we talk about depth, in the atmosphere we talk about altitude, but really it's kind of the same thing. They're both fluids, and both actually give rise to upthrust. If we combine that with weight, or they add together or subtract depending on what's going on, we get sinking or floating. So let's have a look at this idea again, the idea that motion of particle leads to these two things that are strongly related. So once again, collisions, they're crashing into the side of this container, and imagine there's trillions upon trillions of them, so it is effectively a continuous force. You can see it as individual collisions here, but when there's trillions and trillions of them, it's pretty much a continuous force. So pressure is force divided by area. There's a certain set area to this container, and it will give you a certain pressure, therefore. On the other side, we've got the idea of velocity, how quickly something's moving. So the formula for kinetic energy is half mv squared, v being velocity, and this is energy per particle. So that's what temperature is. We met that in a previous video as well. So here we are then, a little bit more detail. We've got here a solitary particle to hopefully make it really clear, and that's moving quite slowly, so it's blue to give us a low temperature. Here it's moving quicker, so there's going to be more collisions, and those collisions are going to be harder. Yeah? So there's going to be more collisions per second or per hour or whatever. At the bottom here we've got a more realistic situation, lots more particles, and obviously in a real situation it'd be many trillions more. So here's a summary of those key points. So we've got temperature increasing, we get more and harder collisions, so it's a double up arrow. More collisions, harder collisions lead to greater force. The area hasn't changed in these two situations, so therefore we get higher pressure. Now here we have what we referred to at the beginning. We see an increase in the outside pressure as we go down in the water, and we can see hopefully very visually here that the bubbles get bigger as they rise to the top. And it's not because there's more air in them or anything like that, it's because the outside pressure has decreased. So hopefully you can see here in the bottom one, we've got a smaller bubble and we've got bigger arrows, so it's going to be more compressed. We can also see that the force is always at right angles to the surface, and that's an averaging out of all those collisions. Now we're looking at volume, which we mentioned a moment ago. So here we've got a certain volume, and here we've got a larger volume. So imagine someone running up and down in a room, and here there's going to be lots of collisions, or many more collisions than there are here. So if the volume goes up, which it does from here to here, the number of collisions per second or per minute is going to go down, so the force is going to go down, so the pressure also goes down. Now we see that in a slightly more realistic circumstance here, lots of collisions here, we increase the volume, so let's say it doubles, then pressure will halve. We'll have half the collisions. Now a slightly more kind of situation you'll get in an exam. Here we've got well, initially one tank, and we open the valve and it spreads to these other three tanks. What happens to the pressure? Well, we can see that the pressure decreases. So 300,000 pascals are all squashed in here. They all spread out. There's going to be less collisions on any particular bit of area, and the pressure is going to go down. Stop the video if you want to check the calculations there. So here again, we mentioned it earlier, the fast compression. Now if we decrease the volume slowly, the temperature can be transferred away, but if it happens quickly enough, we can actually set something on fire, and that's what's happening here, but you can see it in the animation here. What's happening is that the piston is colliding with the particles and giving them energy, hence the increase in temperature. So here we've got the effect of altitude. As you can see here, the board says assuming uniform density, so we tried to model that here, but in essence it's like a pylon. Here we've got American football players. Where would you rather be? I know where I'd rather be. I'd rather be at the top here where I'm not getting squashed. And the same for air particles. If you're at the bottom of the pile, there's going to be more force and therefore more pressure. Now here we have the effect of this pressure, or differences in pressure. A difference in pressure, you'll see on the next slide, leads to upthrust, but we also see it combining with weight. So the weight of an object doesn't change when you put it into water, but how you experience that weight does, because the upthrust will have an effect. So the one in the middle here is obviously neutral buoyancy. Fish deliberately change their density with their swim bladder to make this neutral. Here we've got very positive buoyancy, and here we've got very negative buoyancy, which is a posh way of saying it's going to sink. So as promised, here we've got a visualization of this. So again, as it gets deeper, we have more and more force. Here, hopefully you can see these arrows are the same, but the force on the bottom in this case is going to be greater than anything on top. Even if this is submerged and there's some pressure on top, it's still always going to be less, because we can see it's getting less and less. Now, if we have a denser material here, it's going to float higher, so salty water is denser than fresh water, and the increase is going to be greater, so the object is going to float higher in the water. So here we have a worked example of this idea. So the pressure difference is the height, or the depth, times the density, which we also mentioned, and g, the gravitational strength. Now obviously that doesn't change on Earth, but we still need to factor it into our calculations. So in this example here, 22 meters, density of water, and the board expects you to know g, multiply them together, and we get our answer there. Thank you for listening.